All right, well, as much fun as I'm sure we've been having just taking the derivative over and over and over again, this is our first section where we actually start to see what exactly the purpose of derivatives are and what exactly the purpose of calculus is in the real world. So rates of change are super, super important, and calculus is a very widespread topic. Some of the examples that I've got in this first paragraph here, calculus is actually useful in healthcare, calculus is useful in economics. If you guys ask Mr. Breen, he would be super excited to tell you how useful calculus is in economics. We've already talked a little bit about physics, things like that. So lots and lots and lots of real-world applications, a lot more so than probably a lot of the math that you've seen so far. So we're gonna do a couple quick examples. We've got 2 days on this section. The next section is going to be all about the physics applications, the position, velocity, and acceleration. We're just going to see a couple of quick examples. This first one here, we actually saw one example where the area of a circle was changing, and I know some of us were slightly confused as like what that means. Like, you know, a circle is a circle. But the image that I gave some of you to keep in mind is picture like dropping a pebble into a body of water, or a rock or whatever into a body of water, and then you see those concentric circles kind of move outwards. And so as time goes on, the radius is growing, which means the area of the circle is growing. So the first part here says to find the rate of change of the area A of a circle with respect to its radius. So we're going to write down just the original formula here is the area formula for a circle. So on the AP test, there are going to be a lot of these application problems. There are going to be very few that are just like, hey, take the derivative of this function. And so there are geometry formulas that it's important that you know. Area is one of them, which I'm hoping we know the area formula. There are certain other formulas like the volume of a cone they'll typically give you if they ask you about that. So if you have any questions, just ask. I'll tell you what you would be expected to know and what they'd give you if they asked you to use. So we are looking for the rate of change of the area, or in other words, the derivative of the area, and then with respect to its radius r. So that's the Leibniz notation that we use for this derivative. So the derivative of A with respect to r, or the derivative of the area with respect to the radius. That's how we set this up. So what that means is that we are taking the derivative with respect to the radius of this area function of A. So when we take the derivative here, keep a couple things in mind. First of all, we've been so familiar with x. I don't want it to freak you out that now our variable is an r. It's perfectly fine. Second thing, pi is just a constant. So some people might think like, oh, you know, I've got two different variables. I need to do a product rule or something like that. No, pi is a constant. We saw this one example in the homework that you guys were working on with the last lesson. It was like 5 to the 1/2 times 3 to the 1/2. Just a crazy constant. So don't worry about that. So when we take the derivative here, our constant multiple rule tells us that the pi can just stay out front, and then I take the derivative of the r squared using the power rule. So the power rule says the 2 comes out front, and then r's power technically gets dropped down to 1. You don't ever have to write that power of 1. So when I simplify this up, I get 2 pi r. So that is, we can write that as a prime, we can write that as dA by dr, whatever, but this function tells us exactly how the area is changing as the radius changes. And that formula might look familiar to some of you. We'll talk about that later. So evaluate the rate of change at r equals 5 and r equals 10. So at r equals 5, so remember this notation, dA by dr, and then at the point where r equals 5. So that's the notation we're going to use. So all we're doing is we're taking this formula that we started with, we're going to plug in a value of 5. So this is going to be 2 times pi times 5, which is 10 pi. And they didn't give us any sort of units, but normally you'd say, you know, like feet squared per second or something like that, but they didn't give us any units for this one. And then the derivative of the area with respect to the radius. Okay, so the first one is 10 pi, second one is 20 pi. So when the radius is twice as big, the rate of change is actually twice as fast, which should make sense. I mean, picture the area at 5 is 25 pi, the area at 6 is 36 pi, at 7 it's 49 pi, then 64 pi, 81 pi, 100 pi. As the radius grows, the area is actually increasing more quickly, if that makes sense. The last question here is if R is measured in inches, here we go, here's the units I was talking about, and A is measured in square inches, what units would be appropriate for dA by dr? So dA by dr, so the rate of change of the area, we said would be given in inches squared of area, so keep that in mind. So inches squared of area per inch of radius. So we need to be careful here because normally if you're saying inches squared per inch, you'd want to reduce it down to just inches, but the measurements are different. The inches squared are measurements of area, inches are measurements of radius. So it's like here, it's 10 pi inches squared per inch of radius, 20 pi inches squared per inch of radius. So at that particular point, if the radius were to increase by 1 unit, the area would increase by 20 pi units squared. All right. Second little topic here. This is one of the first calculus topics, actually. It was, Newton, that whole gang that actually created calculus way back in the day. So some of the first questions were all about gravity, free-falling bodies, things like that. So the distance a body released from rest falls, I don't like when they use body. We don't literally mean body. They mean any sort of body, like an apple, like Newton used. Released from rest falls is given by the following formula. So S, it's always our position function, and this is 1/2 g times t squared. So t is for time, g stands for the force of gravity, the acceleration due to gravity, and so we've got the English units versus the metric units. Some of you might be used to the feet measurement, some of you might be used to the meter measurement. We're going to write down both of them. The meter measurement is usually more common, but we'll write them both. So in English measurements, gravity, the acceleration due to gravity is given as 32 feet per second squared. Now this is not something that I'm just making up. If you're physics people, hopefully you recognize these values. So if you plug 32 feet squared right in here, you've got 1/2 times 32. So the formula becomes 16 t squared. And the position would be given in feet. So now keep in mind here, like time is given in seconds, so seconds squared actually cancels with this second squared, which is why the position formula ends up just giving us feet. So that's the English version, and then the metric version, of course, will be given in meters rather than feet. And so if you're talking in meters, the acceleration due to gravity is 9.8 meters per second squared. So that probably sounds familiar if you've taken physics or if you're in physics. The 32 feet per second squared is a lot less common. So our position formula, when you're talking about just a falling position due to gravity, we plug the 9.8 here. 1/2 times 9.8 gives us 4.9. We still have the t squared, and this will be given in meters, because again, the second squared from this piece right here will cancel out with the second squared that's in the denominator here. So two different functions, and this is just the position of a falling item due to gravity. All right, so second example. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, which is about 109 miles per hour, just so you get kind of a visual there. It reaches a height of, here's its position function, after t seconds. So think about what type of function that is. That is a parabola. It's an upside-down parabola because you've got the t squared, but the t squared term is negative. So hopefully that should make sense. I mean, dynamite blast, it's going to shoot it up to a point. It's going to reach a high point, and of course it's eventually going to come back down. Nothing is just going to go up and up forever. We do have gravity, after all, on our hands. So the 160t, this kind of has to do with the initial velocity. That's this 160 right here. So that's how it gets blasted up, and then once it gets up to a certain point, then gravity takes over and it falls back down. That's where the 16t squared comes from. So how high does the rock go? So this, I usually like to do these questions in class, so I can kind of ask you like, oh, what does that mean? How high does the rock go? So what you're trying to reach, I told you guys, it takes on this parabolic shape. We're trying to find this point right here, the peak of position, the highest position. And so what we want to find here, this is where it reaches a maximum, and that means it has a horizontal tangent line. Anytime it has a horizontal tangent line, that means the derivative is 0. So what we want is that the derivative of this function is 0. So now keep in mind when we're talking about position, the rate of change of position is velocity. So we want the velocity to be 0. And think about that. Again, if you're physics people, it's going to be easier for you to wrap your head around these. What's happening is it's going up, and so it's got this positive velocity. It stops for a second. It's not moving just for an instant, and that's when its velocity is 0, and then it starts falling back down. So this is actually negative velocity when it's going back down towards the ground level. So the velocity, like we said, is the derivative of position. Now we've got our derivative rules right here that we can pull. So the derivative of 160t is just 160, because that piece is linear. And then minus, we can do a power rule on this piece right here. So the 2 comes out, multiplies by the 16 that's already there. I get 32. And then the t squared drops down to just a t to the first. So that is my velocity function. That represents the velocity at any given time t. And I want to set that equal to 0. This is going to be just a very simple function. I can add the 32t to both sides, and of course divide both sides by 32. Okay, so for this I come up with t equals 5 seconds. Now always, 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 this is something I'm going to continue to reiterate to you guys with calculus, make sure you're answering the question. They didn't ask for t equals 5, they asked how high does the rock go? So that's a measurement of position. Basically what we're trying to figure out, we just found that the rock turns around and starts falling downwards after 5 seconds, so we want to know at that 5-second mark, how high was the rock? So we're going to plug it into the position function. So the position at 5 is 160 times 5, and then minus 16 times 5 squared. Now this, of course, this is nothing that you'd be expected to do by hand, so you can just plug that right into your calculator, and what you end up with is 400 feet. And that would be the highest position right here that the rock reaches before it starts falling back down to the ground. All right, next, what is the velocity and the speed of the rock when it is 256 feet above the ground on the way up and then on the way down? So this one's a little bit tricky as well. When it is 256 feet above the ground, this is a position value, but when is the question we want to know? So that is a value of t. So they give us the position, they want us to find the value of t. So what we're going to do is we're going to take our position function, 160t minus 16t squared, and we're going to set it equal to 256. And that way what we'll get out of this is we will find the value of time when the position was 256. And then it says on the way up, because again, picture this parabola, it's going to hit that point twice. It's going to be a point over here and a point over here. So that's why they mention on the way up. So we can rearrange this, 16t squared minus 160t plus 256 equals 0. That way we can solve, you can either do the quadratic formula, you can do some factoring. First of all, I don't know if you'd recognize this, but you might figure it out by playing around with some numbers. 256 is actually 16 squared, so for all of these we can pull out a 16. That'll make our lives a little bit easier. So we can factor out a 16 from each term, which means we can actually just divide the 16 out. So if you divide both sides by 16, so we've got a 16 on the outside here, and factoring this, we want to multiply to positive 16, add to negative 10, so that would be a t minus 8 and a t minus 2 equals 0. So again, you could just divide out the 16, set the t minus 8 equal to 0, we get t equals 8, set the t minus 2 equal to 0, we get t equals 2. So again, we want it on the way up, so that would be this value right here. But again, we are trying to make sure that we're actually answering the question that was asked of us. We want the velocity and the speed at this point. So if we look back up here, we've got the velocity function, 160 minus 32t. So we want to know the velocity at time t equals 2. So that would be 160 minus 32 times 2. So plug that in, that's 160 minus 64. That is 96 feet per second. That's the velocity. And then the speed is actually also the same, 96 feet per second. And then it says on the way down, question marks, that's this second point right here. So the velocity at 8, plug the 8 in, 32, 8. So 160 minus 32 times 8. So 32 times 8 is going to come out to be 256. So 160 minus 256, that gives me a negative 96 feet per second. Okay, so velocity, and that should make sense, right? It's at the exact same spot in the function. It should be going up at the same speed that it's coming back down. Now, the only difference between the positive and the negative, velocity takes on direction. So because at this point the rock is going up, we consider it to be a positive velocity. At this point, because the rock is going down, we consider it to be a negative velocity. Now, speed does not take on direction. It doesn't have a sign. It's always positive all the time, whether you're going up or down, left, right, whatever. So the speed for both is 96 feet per second. So a lot of these AP questions love to ask you questions about velocity versus speed. Make sure you know the difference. Okay, acceleration. Okay, so now acceleration, we take the derivative one more time. Acceleration is the rate of change of velocity. So if you're trying to find an acceleration function, you take the derivative of the velocity function. So the velocity function that we had on the front was, let me write this just so we've got it, 160 minus 32t. So this represents the velocity, the rate of change of position. The acceleration is the derivative of velocity, which means it's actually the second derivative of position. So we take the derivative of this function right here, we end up with just a negative 32, because the 160 has the derivative of 0, because it's just a constant, and then the derivative of negative 32t is just negative 32, because that piece is linear. So that is the acceleration. Of course, we want to include our units, so that is going to be negative 32 feet per second squared. See acceleration at any time. So think about that. Acceleration is how the velocity is changing. So the velocity is constantly getting more negative. As the rock is going up, the velocity is positive, but it's slowing down. So that would be a negative acceleration. And then after it turns around, velocity just keeps going lower and lower and lower and lower because it's going down, which means it's which means it's a negative velocity, but it's speeding up as it goes downwards. So the velocity value is getting more and more negative, which is why we've got that negative acceleration. So that is our acceleration the entire time. And then when does the rock hit the ground? So what that means is that we want the position to be 0. So first of all, you're going to have a position of 0 before the blast even hits. So at t equals 0, the position will be 0. We obviously want the second one. We want, once the parabola goes up and comes back down, we want this point right here. So we set the position equal to 0. The position function is 160t minus 16t squared. We set that equal to 0. Now we mentioned before that 16 is a common factor. So we can pull out a 16t. That leaves us with 10 minus t equals 0. So when I set 16t equal to 0, I get t equals 0. When I set 10 minus t equal to 0, I get t equals 10. So now this is the one that we mentioned. That's not the one we want. That's the starting point. We want this point. It takes 10 seconds to go up and then land back down on the ground. So 10 seconds is what we want for this final answer. All right, so that's some of the velocity, position, acceleration stuff. This stuff, very, very, very common on the AP test. Almost one full free response problem is all about position, velocity, and acceleration. So it's really important to be able to read these questions carefully and figure out exactly what they're asking us and exactly how to find what they're looking for. All right, so our last little topic here is about economics. So in a manufacturing operation, the cost of production, so that's our function C, as a function of the number of units produced. The marginal cost of production, that's the derivative. So it's the derivative of cost with respect to units. So cost of production would be, if there were 100 units, that would be the cost to produce 100 units. If there were 7,000 units, C would represent the cost to produce all 7,000 of those units. So dC by dx, that's how much it costs to produce one of them. So now, it's probably not going to be constant, because usually, think even, like our senior gear just came in, the prices change as the number that you're ordering changes. Like to produce one, if we wanted to get just like one hoodie, it's going to cost us a lot more than if we ordered 100 of them. And so the cost to produce that first one, they might have charged like $50 for just one, but if we order 50 of them, they're only going to charge us like $36 each or something like that. So dC by dx, this represents the cost to just produce one. And like I said, that might change depending on how many you're producing total. So suppose it costs, so here's our cost function. to produce X radiators for somewhere between 8 and 10 radiators. So if you plug the 8 in here, 9 in here, 10 in here, that would tell you how much it's costing to produce all 8, 9, or 10 of them. And then R of X, this is the dollar revenue, this value right here. And again, it's the revenue from producing all 8, all 9, all 10. Your shop currently produces 10 radiators a day. Find the marginal cost, and then marginal revenue is a new thing. That's the revenue per item. So to get dC by dx, we take the derivative of this function up here. It's just a couple of power rules. So the derivative of x cubed is 3x squared. The derivative of negative 6x squared, the 2 comes out front, multiplies by the negative 6. So I've got a negative 12 out there. X to the first. Then the derivative of 15x is just a 15 because it's linear. So that is my marginal cost. So that's the function. And then again, it says your shop currently produces 10 radiators a day. So we do want to find that value at 10. So the marginal cost when x equals 10, we're going to plug it right into this function here. So 3 times 10 squared minus 12 times 10 plus 15. So 3 times 10 squared, that's 300, minus 120, that's 180, and then plus 15 gives us 195. So 195, now this is in dollar amount, so $195 per radiator. Now, like I said, if we had plugged in 8, it would have been different. If we had plugged in 9, it would have been different. Things get more efficient usually the more you produce. So that's the marginal cost. And then the marginal revenue, we take the derivative of this revenue function. So again, the derivative of x cubed is 3x squared. The derivative of negative 3x squared, the 2 comes out front, multiplies by the negative 3, get negative 6. X squared drops down to just an x, and the derivative of 12x is just 12. So same thing, we want to find the derivative of the revenue when we're producing 10 items here, so we just plug that right in. So 3 times 10 squared minus 6 times 10, and then plus 12. So this is 300 minus 60, so that's 240, and then plus 12, so that is 252. So we end up making $252 per radiator. So if they wanted to, they could also ask you what the marginal profit was, and the profit is the difference between the revenue that you're bringing in per radiator and the cost to produce each radiator. So we could just do 252 minus 195, so we'd end up making a $57 profit on each radiator. That's a question that they could ask as well. All right, so these AP problems we're going to do together in class because I think that would be a much better use of our time.